Hey folks, welcome to this episode on the activity series. So in this case we have two reactions. The first one actually goes through and creates a full-fledged reaction where we have iron by itself as a metal and copper as an aqueous ion. So in this case copper exists as Cu2 plus aqueous. Now when this configuration kind of occurs, we can see that we get copper metal and Fe2 plus in this sulfate solution. However, if we allow copper to be a metal, in this case solid, and iron to be in a 2 plus configuration in this sulfate solution, what we're going to see is that we get no reaction. Now this is kind of curious. The question is, how we'll be able to figure out if that this reaction will go through, but this one not. And they look very similar. Here we have Fe metal, here we have Fe ion, here we have copper metal, and here we have copper ion. So they look very, very similar. One goes through, one does not. The answer is we have to look to our activity series. So the activity series is just a ranking of the reactivity of metals, and there's also another one for halogens, from usually most to least reactive. Now, for a lone reactant, in the case of the first example, it was iron. In order for iron to displace the copper 2 plus ion in the aqueous solution, okay, when we looked at Fe solid plus Cu2 plus in that solution, remember Cu was CuSO4, so if you kind of break that up, you know it's going to be Cu2 plus, and this is aqueous. For iron to displace the Cu to become Cu solid plus FeSO4, iron has to be more reactive than copper. Now, in this case, we have this table, and this is our activity series, where we see our most reactive metals on the top and our least reactive metals on the bottom. Now, what does that mean? What does that reactive means? Well, the reactivity means how easily these metals lose their electrons. So, metals on the top lose their electrons much more easily than metals on the bottom. So, for example, potassium compared to, let's say, silver, potassium loses its electrons much more easily than the silver does, and therefore it is going to be more reactive. Now, how reactive? Well, it reacts with oxygen acids, but it also reacts with things like cold water. As we go down this list, you'll see that these metals in the yellow, they react with oxygen acids, but they can't react with cold water. They're going to need either hot water or steam to produce hydrogen gas. Again, as we move down, we get even less reactive metals where they don't react with cold water, steam, or hot water, just react with oxygen and acids. Further down, these are really, really unreactive. Some of them don't react with water, steam, or acids. Some of them react with oxygen, and some very, very, very hesitantly react with oxygen. For example, platinum and gold are very, very unreactive. Now you will see hydrogen. Hydrogen is not a metal, but it is used as a reference in terms of reactivity for all of these. So for something to displace something else in a reaction, that more reactive metal has to be higher up on the list than the least reactive, and that way it will displace that one from the ion solution. So here we go. Metals again on the top are more reactive than metals on the bottom, but here is just a little explanation of what actually happens in the background. So let's say that we're comparing calcium and iron, for example. In this case, iron is on this list. Now, you won't really always see this list over here. This is just an example to show what is actually happening. So remember that both of these metals want to lose their electrons. They both want to become, in this case, 2 plus ions. Calcium wants to lose 2 to become calcium 2 plus, and iron wants to lose 2 to become iron 2 plus. But which one will lose the electrons easier, or which one wants to lose them more than the other? Well, calcium is higher up on the list, which means that it wants to lose its electrons more. So that's what's going to happen with calcium. Calcium is going to head and lose those electrons to be calcium 2 plus, and here are 2 electrons. Now, what happens to these 2 electrons? They can't just go into space. They have to be transferred to something else. Well, what are they going to be transferred to? Well, because iron is in solution, it's going to be Fe2 plus. Calcium is actually going to do a little bit of a dirty move here, and it's going to force this Fe2 plus to pick up the 2 electrons that it has lost. So Fe2 plus format, it's an ion, picks up 2 electrons. Well, that now bounces off, gets rid of that charge, and it forms iron metal. So calcium, which was a metal by itself, is now in solution as calcium 2 plus because it forced this iron 2 plus that was in solution to pick up the electrons and form iron metal. So in this case, let's look at, well, if magnesium will displace the zinc. So in this case, zinc is bonded with nitrate, and when you put it into an aqueous solution, it's soluble, which means that it's going to break up into two different things. The zinc nitrate, NO3,2, is going to break up into two different things. One of them is going to be zinc 2 plus, and the other one's going to be NO3 minus. And there's going to be two of those because we can see that 2 over there. And both of these are going to be in the aqueous format. So we first have to see what type of element it is. Well, in this case, it's magnesium. It's a metal. It's going to form a cation. So it's going to displace the other cation over here. So that's why we're asking the question, will magnesium displace zinc? Because they both form cations. So what we have to look at is where are the relative locations of magnesium and zinc. So here, what we see is we have magnesium over here, and we have zinc just below it. So from our knowledge, this reaction should happen. Magnesium should displace zinc. So again, why does this happen? Both of them want to lose electrons, but which one wants to lose them more than the other? That's magnesium. Magnesium will become Mg2 plus, and by doing so, it will lose 2 electrons. Where is it going to lose 2 electrons to? You guessed it, the zinc 2 plus. When the zinc 2 plus gains those electrons, it's going to be forced to form zinc metal. So how does that actually look in terms of an equation? Here we have Mg solid plus zinc 2 plus aqueous. There's the plus. Okay, so going back to here we have our Mg and we have our zinc 2 plus. Now when Mg transferred those 2 electrons to the zinc 2 plus, it forms zinc solid and Mg2 plus. So we're going to have zinc solid plus Mg2 plus. Now, how does this actually look in this reaction? Well, if we put our nitrates back in, we get Mg solid plus zinc nitrate, NO3. I'm just going to leave out the states for now. We get zinc plus Mg NO3, 2. We get a single displacement reaction. Now over here, let's look if copper will have enough reactivity to displace aluminum. So once again, you're not always going to see this one over here. This is just to see what is actually happening in the background in terms of electrons. You only really have to use this one over here. So let's look at copper and aluminum. So we can see that we find copper at the bottom here, and we see aluminum over here. So the question is, will copper displace the aluminum from the solution? So will it be able to displace this Al3 plus? Well, from what we know that only metals that are higher up will displace metals lower down. In this case, it's a metal lower down trying to displace a metal that's higher up. This dictates that it will not actually happen. Okay, so both aluminum and copper want to lose its electrons. Now in this case, aluminum has already lost its electrons. It's Al3 plus. Well, aluminum really wants to lose its electrons. Why would it want to gain electrons if it wants to lose them? So copper's going to say, you know what, I kind of want to form copper 2 plus. That means I have to give away my electrons over here. But Al is going to be like, no way, we're not going to accept your electrons. So copper is going to have to remain as copper solid. Aluminum is going to remain as Al3 plus. And so really what you're going to see is you're going to have Cu plus Al ClO3 to form Cu plus Al ClO3. Now we have the same products as we have reactants. So really, this reaction doesn't exist. We write no reaction. So, using the activity series on the right here, try to predict if these reactions will happen. Now, if they do happen, write out what the ions are going to be on this side. And if they do not happen, then just write no reaction. So take a moment, pause the video, work on this, and we'll come back with the answers. So welcome back. Here are the answers. And the first one, we look at calcium and iron. So we have calcium over here. Iron down over here, the calcium is higher than iron, it will displace iron from the solution. Okay, so this reaction over here is missing the anion over here. This is just looking at the individual ions that are actually taking place in the reaction. This could be like iron 2 nitrate, and then it will form calcium 2 nitrate, but we're just looking at the cations in this case. So yes, it will happen, and so calcium will force its electrons onto iron, creating calcium 2 plus and iron solid. In this case, aluminum and zinc bromide. So aluminum is a metal, zinc is a metal. So these two will be the two species that we're looking at. So will aluminum have enough reactivity to displace zinc? So if we look over here, aluminum is over here, zinc is just below it, so yep, it will be able to force its electrons onto zinc. When it does that, aluminum turns into a cation, so it turns into Al3 plus, and then you get your Br minus. Remember this, cross cross, and you get AlBr3. And zinc is forced to pick up its electrons, so it's going to turn into zinc metal. Question number 3, it shows that there is no reaction. So here, copper is trying to force its electrons onto potassium to create potassium metal. So here is copper, and you can see potassium's all the way at the top here. So copper's trying to move its electrons onto potassium. Potassium's not having it. It's happy as a cation. It doesn't want to gain electrons back, so there's not going to be any reaction. Same thing over here, lead and magnesium. We have lead at the bottom here, magnesium over here. Lead wants to try to turn itself into a cation. That means it has to give it electrons to magnesium. Magnesium is very happy as Mg2 plus, so it is not going to accept those electrons, and there's not going to be a reaction. So that's it, folks. Thanks very much for watching. We'll come back next time with predicting single displacement reactions. Take care for now.